In this video, we show a brief summary of the proposed estimation framework, along with the estimation result in two different experiments. The first is an indoor experiment, which includes dynamic contact events. The second is an outdoor experiment, where the robot walks to make a 160 meters long infinity-shaped loop. This is the overall structure of the proposed estimator framework. We aim to mitigate nonlinearity in the estimation problem by leveraging the group-affine property, which brings the state-independent Jacobian of the residual function. For example, consider the propagation model, which satisfies the group-affine property. For the same noise vector Wi, the uncertainty distribution on perturbed vector space does not change by the operating points, except for the transformation by the adjoint matrix. The group-affine property makes the Jacobian of the residual function state-independent. The proposed estimator with state-independent Jacobian makes less iteration number of optimization and generates smaller estimation error compared to others. Now, with the slip rejection and the contact loop method, the static contact foot assumption is handled in more detail. Legged robot state estimators generally utilize the static foot contact assumption, which assumes that the foot in contact does not move. The slip rejection method handles the conditions where the static foot contact assumption is violated due to dynamic contact events, including slippage of the foot and unstable ground. A large uncertainty sigma s is assumed when the estimated foot speed exceeds the predefined threshold alpha v, whereas a small uncertainty sigma c is presumed when the estimated foot speed is lower than the threshold. Finally, the contact loop method constructs a temporal displacement cost when the calculated foot velocity and acceleration are lower than the threshold alpha v and alpha a. Note that the contact loop method does not apply to filter algorithms that marginalize the recent states. Experiment 1. Indoor experiment with various dynamic contact events. In this experiment, the robot walks in an extreme environment where the static contact assumption is frequently violated. The robot slips on the board that has a low friction coefficient of 0.22. Note that the feet of the robot are sliding on the board when the robot is slipping. Throughout the experiment, the velocity error norm graph will pop up when the proposed estimator and the others become significantly different. It is identified that the proposed estimator shows the fastest decrease in velocity error. As a result, the proposed estimator shows the smallest position drift. The robot walks on a deformable mattress with an elastic modulus of 0.189 megapascals. It is also identified that the proposed estimator shows the fastest decrease in velocity error. The proposed estimator also shows less drift when the robot passes the sliding wood plates and pebble stones. Strong pulling forces are applied 5 times to the robot on unstable terrain. This is the end of the indoor experiment. The proposed estimator showed the smallest error in all error metrics, including orientation, velocity, and position ATE and RE. Experiment 2, 160 meters long outdoor experiment. In this experiment, the robot follows a predefined infinity-shaped trajectory. Although the ground truth position is not given, we can indirectly inspect the proposed estimator's accuracy by comparing the estimated trajectory with the actual bird-eye view map. As a result, the overlapped estimated trajectory aligns with the bird-eye view map. Thanks for watching.